Good afternoon, everyone. So, we will be continuing our studies on discussion on contraction mapping. So, contraction mapping is one of the important chemical engineering mathematical techniques, and that can be used quite widely for determining the steady state of a typical chemical engineering process. And in the last lecture, we have seen that what is the theory behind contraction mapping and how a sequence can be giving a converged how a sequence under what conditions a sequence can be boiled down to a convergent sequence, and it will be converging, a function will be converging to a particular point in the domain, and that particular point is called the steady state or the fixed point of the system. And the steady state is very important, and we are basically going to study what are the conditions of the system that will lead to a unique steady state. Now, we have learned in the earlier class that for a sequence x n, it will be the metric between x m and x n is less than epsilon for sufficiently high value of m and n, and this is true for, since it is true for any arbitrary m and m, the sequence is a Cauchy sequence. But so therefore, the map x is equal to f x, it will converge to a fixed point called x star. Now, we have to prove that this fixed point is a unique fixed point. That means, we have to prove the obtained steady state is the unique steady state. To obtain that, we do the logic of negative reasoning. So, we consider there exists two fixed points. These are x star and x double star. So, therefore, if we calculate the metric between these two fixed point, the metric between x star and x double star should be nothing but metric between this relationship has to be obeyed for both the cases. So, metric between f x star and f x double star, and since we have proved that f is a contraction map, so this should be less than k d between metric between x star and x double star. So, now we can change over this and we can bring this thing on the left hand side. So, the metric between x star and x double star being a scalar, it can be taken out and can be taken as common. So, the equation becomes metric between x star and x double star multiplied by 1 minus k should be less than or equal to 0. Now, this is ever positive. The k is a fraction lying between 0 and 1, 1 minus k is always positive. Then in order to satisfy this equation and this metric which is ever positive, so multiplication of the two positive quantity cannot be negative. So, the multiplication, so the only option that is left is the metric between d x and x double star should be equal to 0 in order to satisfy this equation. So, therefore, the metric between x star and x double star turns out to be 0, that simply means we are talking about the same point. So, x star and x double star, they coincide. Since they coincide, we are talking about that x star is a unique fixed point. So, that goes the so we are talking about the condition of unique fixed point. So, let us summarize whatever we have done till now. We considered X is a metric space and F is a map in space X, then for every value of x and y belonging to space X, F is defined a contraction map if metric between f of x and f of y is less than equal to k times metric between x and y, where k is a fraction lying between 0 and 1. Now, if f is a contraction map, it has a unique fixed point provided space X is complete. So, that goes the mathematical definition of fixed point and the unique fixed point or the contraction map. So, let us look into one of the chemical applications, chemical engineering applications. Typical chemical engineering application occurs in the field of reaction engineering. In this field, what we can do by adopting the contraction mapping method, one can identify the set of the operating conditions for which one can get the unique fixed point or unique steady state condition. So, we talk about a reactor, it is known as CSTR. CSTR is known as continuous start tank reactor. So, this reactor is known to all chemical engineers. It is basically a and it is we to consider a non-isothermal CSTR. It is a start cell where the materials are going into at a concentration CF and temperature TF, and within the reactor it is well stirred. So, therefore, it is assumed the reaction volume or reaction material inside the reactor is well stirred, it is uniformly stirred everywhere, and the concentration that is prevailing inside the reactor is C and temperature T, and the same concentration we are going to get at the output or the stream that we are drawing out. So, Q is the volumetric flow rate, V is reactor volume, and there is a jacket has been placed where we are putting the coolant liquid at temperature Tc. Now, we are considering a first order irreversible reaction is going on inside the reactor, A going to B with a rate constant K. This is first order irreversible reaction, and what we will be doing? We will be doing a species balance for this particular set of reactant A. So, we write down the species balance equation for A, and any balance equation is in the form of rate of accumulation is equal to total rate of material that is going into the system minus rate of material that is going out of the system plus generation rate of generation minus rate of consumption. Now, if we are writing down a balance equation for the reactant A, then there is no rate of generation that is having in the system. It will, the reactant will be consumed, and the rate constant is given by the rate expression, the first order kinetic rate expression, and the rate expression is given as R A minus R A is equal to K times C. Okay. So, we write the balance equation for the species the reactant. So, d dt of V times C is equal to material that is going into the system is Q times Cf minus Q times C that is going out minus rate of consumption will be V times rate expression V times minus R A. So, in V into K into C, that is the how the rate of the reactant that is consumed into the system as a reactant. Okay. And the rate constant K is written as in terms of Arrhenius coefficient as K naught into e to the power minus E by R T. So, that gives the complete expression, and in our whole analysis the reactor volume is kept as constant. So, we can write V times dC dt is equal to Q times Cf minus Q times C minus V C K naught e to the power minus R T. So, this equation is the mass balance equation. It is indeed a solute balance equation. It gives the total balance of the reactant. Next equation that we are going to write is the conservation of energy or heat balance equation. Now, again we will be writing the same thing, like rate of accumulation of energy is equal to rate of energy that is going into the system minus rate of energy that is going out of the system plus rate of energy, which is an exothermic reaction. So, amount of energy that is getting out of it, and the material that is taken out by the coolant. So, rate of energy taking out. So, if you write down the conservation of energy, the first term will be rho Cp V times dt dt. This gives rate of accumulation of energy minus Q rho Cp Tf is the energy by which the energy getting into the system, the incoming stream. Q rho Cp T is the rate by which the energy is flowing out of the system plus minus delta H R V times C K0 e to the power minus E by R T. That is the exothermic, the energy that is rate of energy that is developed into the system because of the exothermic reaction, minus U times A T minus T C energy going out of the system. So, this is the accumulation term, rate of accumulation. This is the incoming energy, this is outgoing energy, this rate of energy generation, and this is the term, the energy rate of energy taken out by the coolant. So, we write down the mass balance equation, species balance equation and the energy balance equation. This is the second equation. Then we will reduce this, we will working on these two set of equations, but before that we should make the parameters dimensionless. So, the variables becomes well behaved within the range of 0 to 1. So, let us do the non-dimensionalization of the parameters. The first non-dimensionalization parameter is the non-dimensional concentration, that is given as conversion. The conversion is given as 1 minus C by Cf. C is the concentration at any point of time, divided by Cf is the feed concentration, 1 minus that is nothing but the conversion. So, we define Y as so conversion is non-dimensional concentration, Y is non-dimensional temperature. This is defined as E over R Tf square T minus Tf. Okay. So, and we defined K as the Arrhenius rate law, e to the power minus E over R T, and this becomes K 0 e to the power E by R T f. We add and subtract. So, it becomes e to the power E by R T f 1 minus T f by T. Okay. So, we can make the let us work on this equation. Okay. So, Y is we take 1 T f inside E by R T f. Okay. We take 1 T f inside. So, this becomes T by T f minus 1. So, R T f by E, R T f by E times Y will be nothing but T by T f minus 1. So, T by T f can be written as 1 plus R T f by E multiplied by Y. So, in this equation the left hand side is completely non-dimensional, and the right hand side there are two terms, one is completely non-dimensional. In this term Y is non-dimensional, that means R T f by E has to be a non-dimensional number. We call that as epsilon, right? Epsilon is equal to R T f by E. Okay. E is the activation energy. So, we write as 1 minus T f by T is equal to so T f by T is how much? So, T f by T is nothing but 1 over 1 plus epsilon y. So, if that is the case, then 1 minus T f by T will be 1 minus 1 over 1 plus epsilon y. So, this becomes after simplification epsilon y divided by 1 plus epsilon y. So, therefore, we can express k as k 0 e to the power minus E by R T f into e to the power 1 by epsilon y divided by 1 plus epsilon y, and finally, this becomes k 0 e to the power minus E by R T f e to the power y divided by 1 plus epsilon y. That is why that is how the Arrhenius rate constant is made non-dimensional. We write down one expression, one assumption here. The assumption is, to simplify our mathematical treatment, we have this assumption. The assumption is E is extremely high. For extremely high epsilon for activation energy E, the epsilon will be extremely small, RTF by E will be tending to 0. So, in that case, if for high activation energy epsilon y will be much less than 1. Under this condition, this expression will be simply reduced to a much simpler amenable form, and what we can do, we can neglect 1 plus epsilon y, and we can neglect epsilon y terms with respect to 1, and this will be simply e to the power y, and the expression of Arrhenius rate constant can be written as k is equal to k0 e to the power minus RTF multiplied by e to the power y. This is known as, this assumption is known as the Frank-Kamenetsky assumption. Approximation, or often that is high that is epsilon is equal to RTF by E is extremely small. This is known as the Frank-Kamenetsky approximation, or since it is appearing in the exponential term, sometimes it is also known as the exponential approximation. Okay. So, under the approximation of Frank-Kamenetsky method, then we can reduce our mass balance equation and energy balance equation to more amenable form. So, just look into the mass balance equation. Whatever we have derived written for the in the earlier case, it will be minus, we make it non-dimensional, minus V times Cf dx dt is equal to q times Cf times x minus V k naught e to the power minus E by R T f e to the power y Cf multiplied by 1 minus x. So, we make the whole thing to be non-dimensional, divide everything by both sides by Cf and by q. So, this will be minus V by q dx dt is equal to x minus V by q k naught e to the power minus E by R T f e to the power y 1 minus x. Now, this whole term thing is non-dimensional, and this is known as Damkohlen number. And Damkohlen number is a parameter, and here also the on the right hand side x is non-dimensional, this is non-dimensional, y is non-dimensional, x is non-dimensional. So, therefore, on the left hand side also has to be non-dimensional. Out of this there are two components, the left hand side is a multiplication of the two terms, the right hand side the t is in second, and if you look into the unit of V by Q, V is in meter cube and Q is the volumetric flow rate meter cube per second. Therefore, V by Q is having the unit of time. So, therefore, we define non-dimensional time as T by V by Q, and this equation can be written in absolutely non-dimensional term as dx d tau is equal to minus x plus Damkohlen number 1 minus x e to the power y. Okay. Next we, so this gives the dimensionless form of mass balance equation. Next we do the same treatment for the energy balance equation. In this case, we make it non-dimensional, rho Cp V R T f square divided by E dy dt is equal to minus rho Q Cp y by E R T f square plus minus delta H r, this is the exothermic reaction term, V k naught e to the power minus E over R T f e to the power y C f 1 minus x minus U a over E R T f square times y. Only one assumption has been made. It has been made that T c is equal to T f. We have this assumption to have a mathematical simplification in our analysis without any loss of generality of the problem. We are assuming that the coolant temperature is getting into the system at the feed temperature, that is reasonable one. So, again we define some of the non-dimensional parameter. B is minus delta H r C f times E divided by rho C p r T f square. This is known as the dimensionless heat of reaction, and we have another non-dimensional parameter beta, that is U a rho C p times Q, and again this is dimensionless heat transfer coefficient. So, the non-dimensional form of the energy equation is, we will be able to write it down now. dy d tau minus y plus b times Damn-Coulomb number E times e to the power y 1 minus x minus beta times y. So, this is the form of in a heat balance equation or energy balance equation in its non-dimensional version, and we have already seen and derived the non-dimensional version of mass balance in the a couple of minutes ago. So, let us just write these two equations in the non-dimensional form. The mass balance equation takes this form: dx d tau is equal to minus x plus dA 1 minus x e to the power y, and dy d tau is equal to minus y plus b times dA 1 minus x e to the power y minus beta y. These two equations are solved the subject, they are subject to the initial condition at tau is equal to 0, x is equal to 0 and y is equal to 0. Now, let us look into the, so this is the transient mass balance equation, transient energy balance equation. So, this is the equation governing with the governing for the concentration. This is the equation which is governing the temperature of the system. Now, we are not interested into the transient analysis. What we are interested in, that we are interested in the steady state process. So, at the steady state, the state variables becomes x s s and y s s, and under these conditions at the steady state, the transient terms dx d tau and dy d tau, they does not exist, they vanish. So, therefore, at the steady state we write down the governing equation minus x s s plus dA 1 minus x s s e to the power y s s, and the energy balance equation will be giving you y s s plus b dA 1 minus x s s e to the power y s s minus beta y s s, and we can just combine, you just write them in a more amenable form. We can write it as minus y s s, combine these two terms, it will into 1 plus beta plus b dA 1 minus x s s e to the power y s s. We can combine these two equation and write it down as, if we combine these two equation, what we will be getting, the resultant equation will be very simple form: b x s minus 1 plus beta y s s. So, YSS will be nothing but B divided by 1 plus beta times XSS. So, simplification of energy balance, non-dimensional form of energy balance and non-dimensional form of mass balance gives a very straightforward linear relationship between the non-dimensional temperature and non-dimensional concentration or conversion through the parameters B and beta, and it is a linear parameter. Now, what we can do? We can substitute y in one of these equation in favor of x and express everything in terms of x. Let us do that. So, if we do that, we will be getting 0 is equal to minus x plus dA 1 minus x e to the power b divided by 1 plus beta times x. So, we can write it in this form. So, this is an this is in steady state. Now, we can do away with the steady state. We substitute x steady state by x. So, if we do that and take this thing on the other side, we will be getting the equation x is equal to dA into 1 minus x e to the power b by 1 plus beta times XSS. Now, there are two ways this equation can be, XSS will be written as x. Now, if we, so this is some function of x. Okay. So, there are two ways this functional form of this function can be written. The natural choice of writing this equation is this, the way it is written. Natural choice, it is written as x is equal to x to be taken on the other side, dA into 1 minus x e to the power b by 1 plus beta times x. Now, let us try to analyze this expression. In this expression, if you see the left hand side, what is left hand side? It is nothing but conversion C by Cf, and C by Cf is always a fraction. Therefore, 1 minus C by Cf a fraction. As a result, x is always a fraction. The domain of x is from 0 to 1. On the other hand, let us, this is the status of left hand side. The status on the right hand side is that in this case dA can be assuming any value up to it is a dA, b and beta. These parameters, they belong to the domain 0 to infinity. If that is the case, the right hand side can be also belonging to 0 to infinity. So, therefore, the domain of left hand side and the right hand side does not match. So, if we take up a value, so if we write x is equal to, let us say this is x is equal to f x, then the x belonging to the domain 0 to 1, where f is a map, it takes up a value in the x domain, operates on it, but it returns a value in the 0 to infinity domain. So, the way we have written x is equal to f x from this equation is not proper. So, what is the so f is not a contraction map in this case. So, if we write x is equal to dA 1 minus x e to the power b by 1 plus beta times x is equal to f of x, this is not a contraction map. Because the domain of left hand side does not match with the domain on the right hand side. So, we have to rewrite this equation from the starting point once again. So, we write it x is equal to dA into 1 minus x e to the power b divided by 1 plus beta times x, and we just multiply this equation by this exponential term. So, this is dA e to the power b by 1 plus beta times x minus x times dA e to the power b by 1 plus beta times x. So, we take x to the left hand side. So, this becomes 1 plus dA e to the power b by b plus 1 by beta times x is equal to dA e to the power b by 1 plus beta times x. So, divide this by this equation. So, we will be getting x is equal to dA e to the power b by 1 plus beta times x divided by 1 plus dA e to the power b by 1 plus beta times x. Now, if we, so this we write down as f of x. If we recast the f of x in this form, we can see that for any value of dA, b and beta lying in the domain 0 to infinity, this will be f x on the right hand side will be always a fraction. This something divided by 1 plus something. So, it will be always a fraction. So, f is belonging to the domain 0 to 1 always, and so for example, if we plot, so what is f x then? F is dA e to the power b by 1 plus beta times x divided by 1 plus dA e to the power b by 1 plus beta times x. For x is equal to 1, x is equal to 0, this becomes dA divided by 1 plus dA. So, this is less than 1. If we put the maximum value of x, f x is equal to 1, this will be dA e to the power b divided by 1 plus beta divided by 1 plus dA e to the power b divided by 1 plus beta. So, this is also less than 1. So, f x for whole domain of x lying between 0 and 1, f x is also lying between 0 and 1. So, really we are now mapping the, so what f is doing now? F is taking up a value from the x domain which is between 0 to 1 and it is mapping on the same domain in 0 to 1. So, the choice of this function x is equal to f x is appropriate and we can go ahead with this. Now, if you look into the f prime x, you will find out that f prime x turns out to be 1 plus dA e to the power bx divided by 1 plus beta whole square. So, for the full domain of x, f prime x is less than 1 and it is ever positive. So, f x, this simply means f prime x ever positive means f x is a monotonically increasing function. Increasing function in the interval 0 to 1. Okay. So, now f can be a contraction map if f is a contraction map, then we have to get this equation to be satisfied. Metric between f of u and f of v should be less than equal to k d times metric between u and v, where metric between u and v is nothing but the distance between u and v. So, it is mod of u minus v. So, therefore, we can write d of metric between f of u and f of v can be written as mod f of u minus f of v, and we can write down the expression of f in this fashion. So, if you remember what is f, f is dA e to the power b by 1 plus beta x divided by 1 plus dA e to the power b by 1 plus beta times x. We substitute b by 1 plus beta as a parameter a. So, f becomes dA e to the power a x divided by 1 plus dA e to the power a x. So, d of metric between f of u and f of v now becomes mod of dA e to the power a u divided by 1 plus dA e to the power a u minus dA e to the power a v divided by 1 plus dA e to the power a v mod of that. Now, we can have a Taylor series expansion. So, we can rebrush your earlier knowledge that what is a Taylor series expansion. F of x can be expanded about a value x naught as f of x naught is equal to f x equal to f x naught plus x minus x naught, f prime x naught plus higher order term x minus x naught square d square f x dx square evaluated at x naught. So, we neglect the higher order terms. So, we expand f of u about v by Taylor series expansion, and the expression becomes f of u is equal to f of v plus u minus v f prime v. So, this is the Taylor series expansion of whatever we have done earlier. So, we just write f of v plus u minus v and what is f prime v, that is the df dx evaluated at v, and that expression becomes a dA e to the power a v divided by 1 plus dA e to the power a v square of that. So, therefore, we can so the expansion of f of u with respect to about v by Taylor series expansion is given by this expression. Then we have the mean value theorem. The mean value theorem, if you remember what is the mean value theorem from our undergraduate level, the theorem said that if u and v, if u and u v is an interval such that w is belonging to u and v, then f of u is equal to f of v plus f prime w multiplied by u minus v. So, we just substitute that. So, f of u minus f of v is equal to u minus v a dA e to the power a w divided by 1 plus dA e to the power a w square of that. That is the case. So, we are in a position now to write it the metric between f of u and f of v more concrete fashion. So, that will be mod of f of u minus f of v. So, this will be, we just write down the this expression from here. So, it will be mod of u minus v a dA e to the power a w divided by 1 plus dA e to the power a w square of that, and mod u minus v is nothing but metric between u and v multiplied by this factor a dA e to the power a w divided by 1 plus dA e to the power a w square, and we write it as a quantity z. So, this becomes z times metric u and v, where z is a function of continuous variable w lying in the domain 0 to 1. Now, this is a contraction map if and only if this z maximum value. So, since z is a continuous function of w, the maximum value of z. So, the idea of that is that if this f is a contraction map, metric between f of u and f of v should be less than k into d of metric between u and v. That means, maximum value of z should be less than 1. So, if the maximum value is less of z is less than 1, then all the values will be less than 1. If that is the case, so we write down the condition for the contraction map for f to be a contraction map, the z max should be less than 1, and if z max is less than 1, there exists a unique steady state. Unique steady state exists. Now, let us find out how z max need to be calculated. Z max will be calculated if we write dz dw is equal to 0. If we have write dz dw equal to 0, that means z is equal to a dA e to the power aw divided by 1 plus dA e to the power aw square of that should be equal to 0. And if you solve this equation, you will be finding out that maximum value occurs at w is equal to 1 over a ln 1 over dA. If you put back this equation in the here, so you will be getting e to the power aw is nothing but 1 by dA. So, e to the power aw is nothing but 1 by dA, and substitute back into the governing equation. So, z max becomes a by 4. So, 1 plus 1 2 square. So, it will be a by 4. So, the condition of the contraction map is z max is less than 1, that means a by 4 should be less than 1, and let us substitute the value of a is nothing but b divided by 1 plus beta less than 1, 4 into that. So, b is less than 4 into 1 plus beta is the condition. So, b is less than 4 into 1 plus beta is the condition for occurring unique steady state into this system. So, contraction map is successfully applied for this particular system, and the among the, so there are 3 parameters we are having, b, beta and Damkohlen number. Let the Damkohlen number be anything. So, if the condition between b and beta, this is the relationship between the parameters b and beta such that b is less than 4 into 1 plus beta, then we will be having a unique steady state into this particular problem. So, this example clearly demonstrates that how contraction map can be utilized to a practical chemical engineering system, that is a continuous start tank reactor, and for which we will be having non-isothermal start tank reactor, which is very realistic in nature, and b should be less than 4 into 1 plus beta, for which the unique steady state will be existing for this system. Next, I will take up a couple of examples to illustrate this use of contraction mapping further in chemical engineering application. So, first example I will be taking up is the is this one. Let us say dynamics of a chemical engineering process is given by this mathematical expression dx dt minus x into 1 plus a square b square x square plus a b x is equal to 0, where the x lying between 0 to 1 and the parameters of the system a b are the parameters they belong to the domain 0 to infinity. They can be assuming any values from 0 to infinity. Now, we examine the steady state of the system and come out with a condition on the parameters, which are basically the operating, a combination of the operating conditions for which we will be having a unique steady state to this system. So, let us first evaluate the steady state. The steady state will be evaluated from this equation when the dx dt will be equal to 0. That is the case, we at the steady state we put dx dt equal to 0, and you will be getting this 1 minus x into 1 plus a square b square x square plus a b x equal to 0. So, x can be written as in this form, a b x divided by 1 plus a square b square x square, and we just examine what is the range of left hand side and right hand side. The left hand side x belongs to the domain 0 to 1, and the right hand side you can find out that this for any value of x between 0 to 1, the function will be having, let us say for x is equal to 1, maximum value of x will be assuming as 1. So, for that a b divided by 1 plus a square b square. So, it will be less than 1. So, right, for any value of x lying in the domain 0 to 1, f of x is also lying in the domain 0 to 1. So, the map x is equal to f x is a proper choice and there is a potential chance that this map can be treated as a contraction map, and we can identify the conditions those will be coming out, or if this map is a contraction map. So, if that map is a contraction map, then we can we use the formula f u minus f of v is equal to u minus v multiplied by f prime at w, where w lying between u and v, and this relationship we get from the Taylor series expansion. So, we make this analysis further. Metric between f of u and f of v becomes z times metric between u and v. So, if you remember what is z, z is nothing but f prime evaluated at w. So, it will be df dx evaluated at x is equal to w, and if you write down this, if you differentiate this expression, this becomes a b divided by 1 plus a square b square x square minus p x to a square b square multiplied by 2 x divided by 1 plus a square b square x square, square of that. So, you can take this as common, and the whole thing becomes 1 minus a square b square x square, and the whole expression on the right hand side will be evaluated at x is equal to w, and you will be having a b into 1 minus a square b square w square divided by, okay. So, there will be square here. So, there is the LCM 1 plus a square b square w square that is the value of z. So, z is a function of w, and we for if this expression the function f to be a contraction map, then z maximum should be less than 1, that is the criteria. So, we differentiate it once again and evaluate the z maximum and put it equal to minus 1 and see what you get. So, dz, if you really do that, you will be getting dz dw is equal to something like this, a b minus 2 a square b square w divided by 1 plus b square a square w square, square of that minus 1 minus a square b square w square multiplied by minus 2 a square b square 2 w divided by 1 plus b square a square W square cube and put it equal to 0 to evaluate the maximum value of z. If we do that, we will be getting 1 is equal to 2 into 1 minus a square b square w square divided by 1 plus a square b square w square, and if you simplify this, you will be getting w is equal to 1 by root over 3 AB. Now, at this w the z is maximum. So, we can evaluate the z maximum as by putting a square b square w square as 1 over root 3. So, it becomes z maximum becomes a b into 1 minus 1 upon 3 divided by 1 plus 1 upon 3 square of that. So, you will be getting 3 a b by 8. Now, for contraction f to be a contraction map, the condition is z max should be less than 1 and we will be having a b should be less than 8 over 3. So, that is the condition for which we will be having. So, this is the relationship between the two parameters a and b, that is a b should be less than 8 by 3 should be there for existence of unique steady state. So, we will be select a and b such that this is less than 8 by 3, so that a unique steady state will be existing in the system. Similarly, we can go through some more examples where in chemical engineering system where the contraction mapping can be utilized, can be applied in order to find out the combination of the operating variables or the system parameters such that unique steady state will be obtained in such chemical engineering system. And we will in the next class we will be taking up some more example to illustrate the use of contraction mapping in chemical engineering. Thank you very much.